This is hi, good morning, everybody, and welcome to this week's seminar. This week we are very glad to have Warren from Princeton, and who's going to talk about this exciting topic, BKL bounces outside homogeneity. So Warren, please take it away.
Well, thank you very much for the invitation. It's really a pleasure to be here. Although it's a bit surreal speaking in front of a mostly online audience. Okay, so I'm going to be talking today about BKL bounces outside homogeneity. So these words may be a little unfamiliar. So hopefully in the first few slides I'll try to introduce what this means. Okay, so let's firstly, okay, I don't know exactly how much of this slide to skip, but let me first introduce the Einstein equation. So in Einstein's general relativity, we solve for a spacetime which consists of a manifold, so it's a four-dimensional manifold together with this Lorentzian metric, which has the signature of minus plus plus plus. And okay, it solves in this talk at least it will solve the Einstein vacuum, which just says that the Ricci curvature of this metric is. Okay, so of course, we want to think about this as a PDE, and okay, I won't say too much about this, but in certain coordinates, say harmonic coordinates, we can write this as a PDE that really looks like a system of nonlinear wave equations. Okay, and because it's a system of nonlinear wave equations, we know that it admits so-called initial value formulation, where if we morally prescribe the metric as well as its time derivative on some initial space-like hypersurface, so this is just, then we can solve for the entire space. Okay, so I won't really describe what these words mean, which most of you already know, but we can find this maximal Willoughby hyperbolic development, which attains this solution. So what I'm going to be talking about today is singularities in general relativity, or singularities in solutions to the Einstein equations. So okay, this has a kind of very long history, but one thing I definitely have to mention are these Penrose-Hawking singularity theorems. Of course, Penrose won the Nobel Prize for this a couple of years ago. And okay, what do the singularity theorems say? They say that under some conditions, which I won't really show you, they predict that space-time, the space-time predicted by the official value formulation of the Einstein equations in the previous slide is. Here it says is not time-like geodesically. Okay, so I do want to say that does not say space-time is singular. But nonetheless, we call these the singularity theorems. So because of what I just said, the theorem doesn't predict singularity in the sense of something glowing, okay, which is the usual PDE sense of the word singularity, but instead it predicts this thing geodesically. And there are actually some cases of spacetimes which fall under the realm of either the Penrose theorem or the Hawking theorem, which don't actually contain singularities. And in fact, they contain these things called Cauchy horizons, where the metric is kind of extendable beyond so-called. So okay, two examples we know of are the Kerr black holes. So the interior of the Kerr black hole ends in this Cauchy horizon. It's actually the part of the spacetime which is predicted by the theorem is just this kind of, it goes up to this point there. And spacetime turns out to be extendable beyond here. That's actually what's predicted by the theorem. So in cosmology, there's also this example of non-spacetime. But okay, I don't really want to talk about those for the rest of the talk. Instead, I do want to talk about examples of genuine singular solutions. Okay. So what do I mean by that? So we have some examples. So one of them is the Schwarzschild black hole. So I've written this in a slightly unfamiliar way. So of course, usually we have these TR Peter phi coordinates. I've now written this the part containing dr squared in this form, and I've replaced the t by x. Okay. Now why have I done that? Because I'm actually focused on the interior of the black hole. So R here will live between 0 and 2m. So in that region, R is a time-like coordinate, and the usual T is space-like coordinate. Okay, so that's Schwarzschild. Okay, the other main protagonist of the talk are the so-called chasm solutions. So these often occur in cosmology. And okay, what are these? So these solutions here, they look a little bit like Minkowski space, but of course there's these funny powers of T or tau in front of the spatial directions. And what are these powers? Well, I'll actually write these things down. Okay, so these PIs, at least in the context of this slide, they're just real numbers, and they satisfy these two Kasner relations, which is that the sum of the three numbers is the squares. Okay. I do want to mention one thing already, which is that, you know, if I just forget, you know, I forget, so there's three of them. Okay, let me forget about all the context and let me just think about these two relations. So this, of course, the sum of three numbers being one is kind of an equation for a plane. The sum of the squares equals one is, you know, is an equation for a sphere. So if you intersect the plane with the sphere, you get a sum. So, you know, in kind of parameter space, we often think of so-called Kasner sum. And I'll get back to this. Okay. So why have I called both of these genuinely singular solutions? So one thing you can compute is curvature. So if you take the question state as a complete contraction of Riemann curvature, you can compute that, you know, in the Schwarzschild case, it blows up as r to the -6 as r goes to 0, and in the Kasner case as tau to the -4. So in both cases, you know, there's actually something at the level 2 derivatives of the metric that's blowing up towards the singularity. Okay. However, okay, you might be worried. You might be worried that, you know, both of these guys, that they're very, very symmetric. They both contain a lot of killing fields, for instance. And okay, there's no reason to think that these guys represent in any sense all singular spacetimes in GR. That's what we're going to need. So
Click on that, yeah. Yeah, I see.
okay. Good. So, okay, well, as I said, we'll be interested in understanding the most general singularity. And okay, from this point of view, the first thing I want to mention is, well, some heuristic works from physics, starting with the work of Khalatnikov and Lifshitz. So what they did is they kind of just guessed, they made an ansatz for the most kind of general singular solution to the Einstein vacuum equations. So they just guessed that the metric takes this form, and what I want to say is that this thing looks a little bit like the Kasner metric on the previous slide, right? There's still the minus d tau squared. Whenever someone comes to okay. But the difference is now that, you know, these exponents, pi, I'm now allowing them to depend on x. So x is the spatial variable, not the time. And also, as well as that, I'm allowing these directions. So previously, these omega i's, they were kind of these one forms. You could see this dxi squared. So now I'm going to let them be kind of arbitrary one forms on whatever spatial space. Okay, so you can ask, you know, I've just written down this ansatz. Of course, you know, I've already said whether it solves the Einstein equations, and this is what Khalatnikov and Lifshitz asked. And they found that, you know, it at least forms some kind of leading order term for some kind of power series solution. So you take some kind of formal power series solution, T, and you ask, you know, can this be a reasonable leading order term? And the answer is yes, given a few things. So firstly, these Kasner relations, so these some of the PIs and some of the PI squares equal to 1. So now, of course, because these things are x-dependent, this is now a pointwise relation. There's also, you know, we need some momentum constraints, which, you know, I won't talk about at all, but here's the important thing. They see that whenever any of these exponents is negative, then the course, you know, if say P1 is negative, the corresponding one form omega 1, in order for this to be a reasonable, you know, leading order term, it has to be integrable in the sense of so hypersurface of polynomials. That's, you know, that's equivalent to this extra differential equation. I want to mention one thing already. So if I have any PIs that satisfy these relations, then you'll actually notice that one of them has to be non-positive. Because, you know, if you have three numbers between 0 and 1, that sum to 1, you square the negatives, right? So one of them has to be at least, well, okay, 0 or negative. So, you know, this always is at least one distribution.
So how does Schwarzschild fit into this?
So Schwarzschild, so in Schwarzschild, you can think of this as d theta, or say d like sine theta. And in both cases, you'll see, so the p corresponding to the dx of the t, -1, and the other two will be 2. So actually, whenever you expect like two directions to be the same, so whenever you expect two directions to be the same, so Schwarzschild, that's true, just that's true. Yes. So, okay, here's the funny thing. So by some kind of heuristic function counting, degrees of freedom counting argument, so in that paper of Khalatnikov and Lifshitz, they actually suggest that the final integrability condition, that thing at the end, actually generically doesn't. So actually generically that ansatz is not. Okay. So instead, so now Belinski joins the team, and instead they together propose something called an oscillatory or sometimes called a chaotic approach to singularity. So okay, to explain what that means. So firstly, what they do is they suggest that these pi's and these omega i's are allowed to depend on time as well as on x. So that kind of is completely meaningless because okay, you can really write any metric like that. But they really say something else. So they make this assumption of asymptotically velocity term dominated behavior. So sometimes in the literature this is shortened to ADTD. And what that really means is that whenever we write down any equations, we're going to hope that any terms with time derivatives are much more important than terms with derivatives. Okay? And the reason why you might make such an assumption is if we have, let's consider our singularity. So let's say our singularity lies in this line here. So I'll put my singularity to the past. Then, okay, let's say we have two different points on the singularity, and we draw kind of the light cones emanating from these kind of idealized points. Then you'll see that whatever happens near this point, so that can only really be affected by this light cone, and whatever happens near this point can only be affected by this one. You'll see that because the two light cones eventually separate, that the dynamics towards this point and the dynamics towards that point should eventually come. That's exactly what I mean by dx derivatives eventually. Okay. So okay, you might argue to me that this is only true if this singular boundary is space-like. So in fact, it's this kind of term is what it it's kind of a quantitative statement of singularity being space. Okay, so okay, let's just make this assumption, and let's make this assumption in a very strong way, in that we just write down the Einstein equations in this gauge, and we just throw away the terms. Then okay, what that actually means is that that we have a spatially homogeneous system, right? All points in space are the same, and for solutions of the Einstein equations which are spatially homogeneous, okay, we can kind of change the Einstein equations to a system of nonlinear autonomous finite. Well, just say a system of nonlinear ODEs. Okay. So okay, this exact system of ODEs, it doesn't really matter what they are. Think of the ODE variables, roughly speaking, being the PIs. Okay. Okay, so okay, if we have a system of ODEs, what can we do? Well, we can study, say, fixed points of the ODEs. We can study kind of orbit, the stability properties of fixed points, and also, what happens to kind of generic orbits. Okay, so what I want to say is like one important group of fixed points is it turns out to be a circle. Okay, and that is exactly this Kasner circle, right? So actually, every single one of these fixed points in some sense corresponds to a Kasner space. Okay, so it turns out all of these fixed points are unstable. And moreover, they're unstable with exactly one unstable direction. So, that I guess
is it circular in the piece, or is it just also
it's a circle in the space of these guys, whatever these guys are. It's some large dimensional system. Okay, so I'm claiming in the large dimensional system, each of these guys is unstable with one unstable eigenvalue. And I'm saying if you follow that unstable eigenvalue, so you shoot out, say, what's called the unstable manifold, and you shoot it out, and what it's going to do is it's going to connect this point. So this is what in ODE theory is the heteroclitic orbit connecting one fixed point to another one. And I'll often also refer to these as the bounds, BKL bounds, cascade bounds. So okay, let me think about this a little bit more. So of course, this fixed point here is now also unstable. So that means what I can do is again shoot out another one of these guys, so another bounce. And it turns out that this will just carry on. And this is what I mean by chaos. Okay, so in the language of the PIs, if you really want to translate, you can actually compute exactly what the transition is to go from one Kasner-like fixed point to another.
Is this direction stable direction for you?
So actually each of these guys has two stable directions, and one of them is this. Because actually there's always another. Okay, so I've talked about these very particular orbits that connect one fixed point to another. So, one thing you should actually ask is what happens to a generic, what happens to the star orbit? So, what's actually widely believed is that the generic orbit, what it will do is it will kind of eventually get close to one of these fixed points, and then what it's going to do is kind of follow this unstable, follow this bounce, but then it's going to see the instability here, and it's going to follow that one, and it's just going to. Okay. Now this diagram is getting way too messy, so I won't refer to that anymore. But okay, here's another picture. I mean, I'm just saying that here's like a cascade of such bounces, and here's this generic orbit. Okay, and there are some partial results in this direction, although there's still a lot of interesting. Okay, maybe I won't say too much about this slide, but it's also interesting to ask what happens if you also couple to matter fields. So in subsequent works, I actually the title here, I can't see it. It should say something like matter doesn't matter. But okay, it turns out that if you couple Einstein to most matter fields, it doesn't actually affect this picture I drew. Matter doesn't really have much of an impact on the other side.
Good trick again.
Okay. However, what's important that there are some very special types of matter fields. So this includes, the scalar field, any kind of really scalar field, or say this perfect fluid where the equation of state is the p equals the sound speed is 1. So in those particular cases, those matter fields do actually modify these dynamics, and the effect really in this picture is that there's actually new fixed points in this picture somewhere, and those turn out to be stable. But I won't really say too much. I do also want to mention in physics there is this interesting analogy to billiards. So okay, this as I say, this dynamical systems approach is valid for homogeneous spacetimes, and it certainly has received a lot of attention. But one missing ingredient is actually how we got this picture in the first place. Why we're allowed to throw away this TX. Okay. So there are some, works in this direction, but only in settings where, like in the previous slide, instead of having a dynamical system, unstable fixed points, we actually have systems with stable. And let me not say too much more, but this includes this class of results called, these results are often called stable Big Bang. So what these are is you take, a specific Hasna spacetime with certain some kind of extra stability property, and you show that the singularities, the structure of the singularities.
They have only same direction.
So what happens is so if you add a scalar field, instead of there just being a circle, there's actually really a sphere.
There's the
And in the sphere, some of those okay. Okay, there's also another interesting thing you can do, which is that if you start, instead of taking initial data and solving towards the singularity, you can start with data on the singularity and try and find, what you can do is you can write down that ansatz that BKL wrote down, and you can try and find an actual solution to the Einstein equations that achieves that leading one. So that's been done also in various settings. But I want to say that basically all of these results, we never see any of these bounces. And in fact, the fact that there are none of these bounces is used in a very critical way to actually take care of the next DX. So what I actually want to do is I want to describe some new results where we describe like a wide class of spacetimes, but we contain a singularity, which are ahomogeneous and contain a singularity, inhomogeneous and contain a singularity, but which also actually exhibit at least one of these bounces, at least one of these transitions between an unstable fixed point and a fixed point. And secondly, also exhibits this ABTD behavior where somehow we can still say that in terms of the X derivatives. Any questions? Okay. So, okay, I'm going to describe this set of results in something called Gaudi symmetry, so I should firstly explain what this is. So, I won't really give a geometric definition of this. What I'm going to just say is a T2 Gaudi symmetric spacetime is such that you can write it. Okay, so the metric can be written in this form. And where these functions that are left, so lambda, p and q, they depend only on two variables, so it's t and so the reason why the metric looks a bit funny is because actually it turns out if you write a metric like this, the Einstein equations, the Einstein vacuum equations look very similar. So what this actually looks like is we have a system of two semi-linear wave equations. Okay. Yeah. Okay. There's also equations for lambda. So you can think of these as constraint equations, but we don't actually have to worry about them because you can see that the P and Q equations decouple completely from lambda, and lambda can be solved. Okay. So yeah. So we'll only think about the first two equations. Well, I do want to say one thing. I need to make there's an even more special case where if you also assume that Q is 0, so the second equation here becomes relevant, and the first equation actually becomes linear wave equation. So this is kind of the simplest possible case, and we call this polarized. Okay, it turns out that those two equations for P and Q can actually be viewed as a very interestingly as a system of wave maps between a domain which is 1 plus 2 dimensional and a target which is actually hyperbolic space. And okay, it turns out that those equations for P and Q are exactly the wave map that this system, if you assume the wave map is independent of this addition variable. I don't really want to say too much more about that, but it turns out that this kind of very, very nice geometric structure means that we can show that given any kind of initial data, we can solve for the entire space-time in the interval t, in the complete interval t. So we have global instances. So what we're actually interested in is understanding, what the singularity looks like, and that actually corresponds to understanding the asymptotics of t. Okay, so let's talk about asymptotics as t goes to 0. So we'll first do the very easy case. So if we study the easy case of the polarized Gaudi, so this, remember in that case, we just have a single wave equation for P. And it turns out that we can actually describe the asymptotics completely. We can really say that P looks like some coefficient times log T plus some reported term error as T goes to 0. And actually, I want to make already the observation that that's exactly if you ignore the terms below 1, then if I just erase this term, then that's exactly the solution. So this is actually already a manifestation of this ABT. Okay, but actually I'm really much more interested in the case where there's also Q because this kind of is boring. And okay, this remarkable result of Ringstrom says that for kind of in some sense generic solutions to the equations I had before, then we also still in some sense have the above asymptotic. We still at least have that minus TDTP converges to some number for all values of beta, except there's a few additional things. So firstly, I want to say that in these generic spacetimes, this V beta is actually constrained to lie between 0 and 1. And also that there are some very special points theta, so some finite set of points where that doesn't happen, where either maybe this I think this all so for example that doesn't happen. So I'll get on to why that is later. So it turns out that because if we know that this V theta exists, that we can formally associate, we can do some change of variables and formally associate these. So we can relate it. Okay, so where did this condition that V theta is less than 1 comes from? So, okay, if you look at P2, you'll see that V theta greater than 1 corresponds to P2 being negative. And that means that if we believe, BKL, that means this form, this one form omega 2, should define this way, should be in some sense integral. Okay, so it should satisfy this relation being 0. But it turns out that in general, as long as Q is allowed to depend on beta, then that's why we expect that.
So how does results of
I'll draw that. Okay. So what about this finite set S of points where p theta is allowed to be discontinuous, for instance? It doesn't have to lie between them. So these things are called spikes, and there are actually solutions containing such things, and they can be considered as very, very special points where this thing is zero. For example, p prime vanishes, and that means that at those very, very that finite set of points, this is true. Okay, so I'll tell you what the problem I'm interested in. So although Ringstrom, very, very effectively characterizes kind of the asymptotic behavior as t goes to zero, what I'm interested in doing is I'm saying what happens if I prescribe data away from zero, but such that the corresponding thing, the thing that converges to this v theta. So let's say I initially don't prescribe it to be between zero. Let's say I prescribe it to be then I'm interested in saying, well, that means that something has to change between that time where I set the initial data and t. I'm kind of interested in understanding what happens exactly. Studying things. So let me just draw something. Just how am I doing on time?
You go half now, please.
So okay, so what do I want to do? I want to describe kind of initial data for the Gaudian equations, those wave map equations for P and Q. I want to prescribe the data at t equals t naught, which is going to be away from the singularity, so away from zero. And I want to say that they exhibit up to one of these balances. What are kind of the goals I have? So I want the maximal path development to contain a similarity. I want to include initial data, which is not at first glance compatible with Ringstrom's system. So I want to say, for instance, the data for this minus t away from singularities. I want to understand if something. So I want to say if something interesting happens between 0 and t naught, then I really want to understand this as a BKL balance. And I want to include everything that is very spatial. So let me just draw some pictures. So it's much easier. So as I said, I want to prescribe data here away from singularity. Okay, and then I want to solve it out there, and I want to say what happens. So the easiest case of this is the linear wave equation case. So I consider polarized Gaudian where Q is Qs. Okay. So what happens in that case? Let's say I prescribe little p beta to just be this minus t dtp up here. So this thing has to converge to b as t goes to 0. Well, actually, unsurprisingly, as long as t, as long as we set t0 sufficiently small in some sense, then whatever b is at the end of the day, it should be very close to this. Actually, that doesn't matter in this polarized case where we just have a linear equation. It doesn't matter what we set p to here. Okay, so in the next kind of case where I now allow q to be non-zero. But I also, and then I prescribe this p to be between, but now I prescribe p to be compatible, right? So I can prescribe it to be between 0. Then if I solve down, then the eventual value of b I get at the bottom turns out to be close to this. Again, unsurprising because this is completely consistent. So here's the kind of case I'm more interested in. So let's now prescribe p to be kind of inconsistent with Ringstrom's theorem. So let me say I prescribe it to be. So at least for kind of generic values of q, we can't expect that this will be say the eventual value of b will be close to this as t goes to 0. Okay, so what actually happens? So what actually happens is somewhere in between this minus t transitions from 4/3 to around 2/3, right? And we see this 2 minus p here and data. This is modular these funny spikes. So you remember I said that there's like a finite set of points where b is a lot of jump. So at those points, it'll still be there.
So what was again the theorem of Ringstrom's?
So Ringstrom's theorem says that this object exists. This is the limit minus t to t. Ringstrom's theorem also says that for generic such things, it lies between 0 and 1, all but finitely many modes. So yeah, I mean, one thing to notice is that the polarized case is non-generic. Let me.
So that's why polarized case will be Q0, so that's why.
Okay, and I do want to also say that there's no reason. So okay, in the previous slide I said this to be 4/3. So it turns out I can actually set it to be anything between 0 and 2. By the 2 later. So again, if I do the same thing, well, I see that it's fine. B can be close to P theta, remain close to P theta whenever it was actually initially between 0 and 1. That's this case here. But if it was initially between 1 and 2, then it has to do this balance where it goes to 2. Okay, in either case, it ends up being less than 1, so it's consistent with ratio. And modulo is. So now let's kind of make this very precise. So okay, what am I doing? So I'm prescribing data at t equals t0. So let me just say that this is just p, q, and the time derivatives at initial data. Okay, and I want to make some assumptions. So firstly, I need to assume some probability bounds, which says that, for example, this initial value of minus TPTP is positive, and it's not only positive, actually, it's between say. It's between 0 and 2, right? So I'm saying that 1. Yeah. So okay, what this says is that it's between 0 and 2 in a quantitative. Okay. I need some very, very high order type of L2 bound. Okay. And then what I'm going to do is I'm going to say that for all those pictures, I said that this only works if I choose my initial time to be close enough to the singularity, and it turns out I need to choose my data to be close enough to the singularity depending on these parameters.
What's this?
I will. Okay, don't worry too much about those words. Just think about this element. This is just like an element. Okay, so what are the things I say? I say firstly that AI can, if I solve all the way towards the past, then I can propagate those elements. Firstly. And as even just as a result of this, you can say that this B theta actually exists, the all data satisfy those assumptions then, and also this thing, this the level Q as well. Okay, but that's kind of one thing. But the other thing is that we actually do see these bounces. And what do I mean by that? I just define certain objects, and I just should say that on constant theta curves, or more generally, actually, basically any time like these objects satisfy some nonlinear up to similarity. Okay, and the error terms really do go to 0. It goes to 0 this way. And then, like I can understand bounces just by understanding orbits of this system, which are four variables. Okay, so let me make some comments. So in the class of Gaudy spacetimes, this so understanding that the solution exists. So what I call global class existence means the solution exists all the way to the singularity. So that's true kind of for free because of that geometric structure I told you about earlier. The real content of the first theorem is about the quantitative estimates. It's about saying that I can propagate them. Yeah, and in really in other settings, understanding like even getting global existence is really part of the problem, and it would be really derived as a consequence of propagating such. So in fact, we have I have a related result in the system. It's surface symmetric Einstein Maxwell scalar field system where I do it. Let's not say anything about this. So I want to say that combining with Ringström's generosity theorem, then that's how we get the pictures from this. I am still interested in understanding the setting where minus TPTP is allowed to be above 2. So this is often high velocity in Gaudy. And I think this would be a very, very important step if I want to understand more than 1 bound. So in all my results so far, it's just exactly up to 1 bound. If I want to understand more about things.
Does that correspond to B is higher than?
Yes. I can explain. So let me say a few words about. So both of the theorems are proven simultaneously, and there's kind of three main steps, and it's kind of actually very much in line with. So the first step is understanding the nonlinear ODEs, right? So remember we define these. We define these variables that I called curly p and curly q on the previous slide, and I just want to just let's say I just throw away the terms already, and I want to say that these objects obey some system of nonlinear ODEs, and I propagate L infinity bounds just by understanding solutions. Even though they're nonlinear ODEs, maybe I still bound. Okay, the next hope is I want to say something about the L infinity. Sorry, I want to say something about the spatial derivatives, the theta derivatives. So let's think about what the best possible thing could be. So the best possible thing is that if I just hit this, if I could just compute this equation. So what do I get? Right, the left hand side is fine. The right hand side I apply the chain rule, and I just see that I have some df applied to. So what actually is this equation? But if I ignore the error, what this equation is, it's a linear equation for the first derivatives, for these derivatives of beta. Except, although it's a linear equation, but the coefficient here, this coefficient matrix is it comes from like a solution to this nonlinear system. But nonetheless, we're going to hope that we can use such an equation to derive some kind of estimate for the derivatives of these. Say, for instance, that maybe they are allowed to blow up, but they blow up. They blow up, at a rate which is like t to the minus sigma small. So what I want to say already is that if that's true, what that morally says is that every time I take a d derivative, I cost t to the minus sigma. Okay, whereas of course the t derivatives cost 1 power t, right? And that's exactly what I mean by d theta derivatives, dominated by dt. So that's the heuristic.
So the ODE analysis is that just the BKL, like the bounces, like what's the?
Well, I mean, like adapted to this symmetry class, yeah.
Do you get like more bounces in the ODE analysis if you assume? Do you get like all the bounces if you assume?
So I mean, after putting in Gaudi symmetry, the system of ODEs has changed. I mean, again, that you can see multiple bounces, but you have stable. So it's not as rich as what you can see. Okay. The last step is actually dealing with these error terms, and it turns out because I've written these things as ODEs, the error terms are top order in terms of derivatives, of course. So actually, in order to control these error terms, I do need some kind of energy estimate. Turns out I'll need this very high. Okay, so let me put this into practice. So basically, I'll kind of describe the scheme of the proof just using the single wave equation. So I'm going to treat lots of terms as error terms, including these top order terms, right? That top order term, that top order term. I'll treat them as error terms, and I want to derive ODEs. So I just take TDT of curly p. So curly p is minus TDT. If I take TDT of that object, so I get minus this side. So I just get this right hand side here. So I'm treating that as an error term, but actually also treating that as an error term. And this now takes this curly q switch. Signs maybe. Good. Okay, so that's TDT of this curly p. So now what about this curly q? So I want to take TDT of this. So if I take TDT of this, I can hit the e to the p, or I can hit the t. Right, that gives me that's what gives me this 1 minus curly p here. Okay. I can also hit this term. If I hit this term with TDT, it turns out I treat that term as an error term. So again, I will really explain why. That's how I write down that system. So it turns out this is a very easy system of ODEs to analyze if I throw away the error. It just what I get is this picture on the right, and I see that I have this line. I have just a line of fixed points when q is 0. Okay. And I can see that the fixed points are stable when P is bigger than 1 and unstable. Sorry, unstable when P is bigger than 1 and stable when P is less than 1. And it turns out that basically the entire dynamic picture is that the orbits just connect these unstable fixed points. And they're actually semicircle. Okay, and that's actually because they're semicircles centered around 1, that's exactly why we see these bounces from alpha to 2. Good. Okay, so now let's do step 2. So what I'm doing here is I just take this system of ODEs without the error terms, let's say, and I just commute it with D. And okay, if I write this as a matrix, I get something like this. Okay. Okay, so what kind of things can we say? So of course, if this matrix was constant, so it's constant, for instance, when P and Q correspond to fixed points, right? Then understanding how this behaves is very, very easy, right? I do some kind of maybe matrix exponential type thing. And what you find is that, you know, these derivatives below as t to the minus sigma, where minus sigma, okay, this it just says minus sigma is, say, the most negative eigenvalue of. Okay, so here's a comment. So if you know, remember my goal was to say that this sigma is less than 1. That's going to be true, but only if this P isn't too big, right? So if remember, okay, fixed points are when Q is 0. If P is bigger than 2, then the most negative eigenvalue of this becomes problematic. So that's why I have this extra section. Good. Okay. So of course, in reality, this matrix is not constant, right? You know, it depends on some complicated nonlinear orbit. But okay, the key is that, you know, for most of the time, in some quantitative way, for most values of t, it's actually very close to it. Because it's close to a fixed point, I can still get it back. So okay, close to meaning either close to an unstable or close to a stable one. Okay, so good. That's how we did part 2. So now step 3, we want to throw away these top order terms, treat them as derivatives. Okay, so again, you know, we want to do some kind of energy estimate. But okay, let me first say the goal. Okay, remember my goal was to say that that every d theta costs exactly t to the minus sigma, right? So I want to say that this whole thing, because there's a t squared in front, it has this t to the 2 minus 2 sigma, and that's why it vanishes strong things to use. That's my goal. So okay, let me now try and do the energy estimate. So what I'm going to do is I take that wave equation to P and I just hit it, I commute it many times. Okay. So I get you know a mess, but here's some. Okay. So if I just define like a k order energy, and I understand it's TdT derivative, let's see what happens. So okay, firstly, this term goes away by integration by parts, so that's fine. So what about this? So what this guy here, that guy here is exactly curly Q. And remember that in step 1 we said that curly Q is bounded, right? Because it lies in semicircle orbits. And what that actually means in practice is that, you know, we get a term like this, right? So TdT of the energy, you know, there's a term which is exactly some constant times the energy. And importantly, the constant doesn't depend on how many times. Okay, that's one thing. We also have terms like this. So here we have to use step 2. So we have a term like P. So in step 2, we bounded these types of terms by T sigma's 2. Sigma's less than 1. And okay, if you apply that to the energy estimate, you get a term which looks kind of similar, right? You have also something that flows. Okay. But you know, the lucky thing is that any term which sees a term, anything which sees a term like that in an energy estimate actually, you know, doesn't see the top order energy. It will see instead a term which is 1 order. So okay, instead k minus 1 order. Okay. As I said, the really important thing is this A star turns out to be independent of how many times you differentiate. Everything else, the other constants, they don't. So. Okay. So the benefit of this is that now we can just use this and use induction and integrate this to get a bound on the energy. And what we find is that the energy at the k order blows up. So even at k equals 0, we already blow up at this t to the minus 2a star. But like like every time we differentiate once, we get an extra -2. But it turns out that's basically exactly what. Okay, and to explain why, okay, so remember that error term we wanted to throw away being d((squared p).
And say that's the initial data or what is it?
Oh, sorry, yeah, that is initial data. Yeah, that's the energy of the machine. Okay. Okay, so this second derivative, the term that we wanted to throw away, so we want to throw away in infinity. So what we do is we use some kind of interpolation, right? So this is just sub-level interpolation. Okay, so we can bound it between an L-infinity norm on P and the top order, so kth order L2 norm. This. So this is a term in the energy of K. Okay, whereas P, remember, okay, we actually, so remember curly P is kind of TBT. So we actually only bound P by log T, but that doesn't make sense. Okay, so the important thing is, okay, we see this kth order energy, right? So we see -2a star minus 2 sigma k. Okay, so, but there's a very nice exponent, right? The exponent here has a 1 over k. So what that means is that as we make k large, this -2a star kind of disappears. So you can make that a small one. And okay, because you're also dividing -2 sigma k by k, that's you get exactly -2 sigma. That's the thing we expected, right? That's the thing we expected when we said that each decrease costs. So okay, so that's how we get such a thing. So okay, if you make k large enough, then you can make this delta as small as you want. So t squared. So that the error term we wanted to say is really of that size. It doesn't need much. Okay, so this kind of hierarchy of energy estimates is a very robust method, and I mean there's no reason why this only works in symmetry, and there's applications in other settings such as my companion paper, so symmetry or even just these types of stable comparisons. Okay, really the major difficulty in this whole procedure is finding the correct ODEs to study. So it's more like step 1 and step 2, right? So it's finding the correct. It's finding kind of the correct system of ODEs like that, and then finding the correct system of ODEs like that such that you can study the orbit interval and then also study linears. But anyway, if with that in mind, let me kind of present some kind of potential future directions. So okay, firstly, it'd be nice to understand examples even in this Gaudi setting, which exhibit more than one bounce. Okay, so as I said, that might be related to understanding this high velocity regime where -TTP is allowed to be bigger than 2. And I want to say that there's lots of kind of numerics in this direction for various people. Okay, so if I now go completely outside of symmetry. So let's say I want to understand bounces in the kind of full 1+3 setting. So, but let's say I don't want to understand this chaotic thing, right? This chaotic setting of BKL is kind of complicated by understanding even B's and ansatz. Still lots of problems there. So I can kind of get rid of that by instead studying these Einstein scale. So in there,
Because there's to stable.
Because there are stable points, so we can. There's also still unstable. Still get balances from this.
And from unstable to stable,
yeah.
So again one.
Okay, but okay, the kind of new difficulties here is, of course, just the system of ODEs gets much bigger. I mean, it's a larger dimensional system, and in particular, it has to encode how directions, how the actual frame, like the one forms change during bounces as well as. And also, what's not really understood at all is what the analog spikes are outside of symmetry. Lastly, if I do really want to probe the chaotic setting, there is kind of a good place to do it. So that's this T2 symmetric Einstein equation. So this is a kind of mild generalization of Gaudi. And okay, this has been explored in paper of Seyberger, Eisenberg, Weaver. And okay, in such a setting, you can hope that we can kind of explore regimes where we have infinitely many and therefore some kind of chaotic cascade of such bounces. Kind of, this step-by-step procedure hopefully provides kind of these steps towards understanding BKL's proposal in general. Okay. I think that's
The time for questions from the Zoom audience, from the actual audience.
People ask on Zoom.
Yeah,
Is there any?
there's no question. Yeah. Is there any question from the Zoom?
Are you muted?
I mean,
So in the scalar field case, you said something that you can only have one boundary, is that correct?
No, you can have as many.
Because
Because remember the scalar field in particular, I mean, vacuum is included. It's
no, but I meant in spherical symmetry, your other work.
Yes, yeah. So in spherical symmetry, symmetry actually forces you to.
And but the Gaudi knows.
Yes. The symmetry case, so that case I'm more interested in because you can have applications and say spherically symmetry black holes. That was kind of
So what do you want to show there? That you for generic singularities, space. That's literally how far are you?
yeah, something about understanding generic space. Asking a question. Sorry, I can't hear.
It's muted, right?
yeah, I'm trying to unmute him, but like, he doesn't.
What?
He left. Well. Yeah, I'm trying to unmute him. From the Zoom, any more questions? You start?
I don't have any questions, but maybe you can just.
Yeah, one. So this is actually very interesting.
Yeah.
I don't know much about this, but once you go out, start going out of the symmetry, or maybe, yeah, that's the. You have like any sense of like whatever if you start talking about like other topologies like.
So in this direction, everything should be very local. So it
Doesn't matter on topology.
Yeah, I mean, okay, in the current kind of a lot of the current approaches to actually understanding it, you can't quite explore that everything should be local because a lot of the gauges are local. But the idea is that it should.
What's your next? What's your next?
So okay, I think I can. I think I can. Like the first thing I think I can try.
So right, so this is that you start off with like b whatever being bigger than 2 or so.
Yeah, so it would be like saying on data you start off with this minus TDTP bigger than 2 or bigger than anything. Yeah, you want to understand what happens.
And like every time there's a bounce, it sort of reduces by 1. Is that function?
Yes, that's roughly true. Yeah. So okay, I mean, in that setting, I mean, it's like okay. What really happens is that you add a new ODE. That extra variable, because okay, from that picture I drew with these circles, you see that when it goes negative, that should.
Can you explain it again? Sorry.
So I'm saying if we just have these 2 ODE variables, I have this picture, right?
Right.
So you see, so a bounce is taking something bigger than 1 to but that's just because if I just have these 2 variables, then I only see this one direction. But it turns out that it's like what actually happens is this guy that I treated as an inheritor is not inherited if I allow P to. And if P is negative, if curly P is negative, then actually that guy is responsible for another instability which passes like that. It's another semicircle. And what basically happens in those general cases, which is these two terms. But yeah, I mean the real, but that's not the real difficulty. The real difficulty is it's like throwing away the heuristics because we don't have this.
But you try to still, because the linearization is different, or you have to linearize around those.
So okay, this is what but you basically, I think what you can do is you can add additional. You still linearize, but you have to kind of also take into account like higher order derivatives. As in, I linearize at the level of understanding, say like t squared d. I'm just saying I commute more times with the same vector for t. And then
So that would treat sort of theta as like almost as bad as t. So
yeah, okay, again, I need to.
No, sorry, it's
that's the kind of goal.
work in progress.
I don't want to say too much. One thing I'm certainly very interested about is this. So what I want to do here is like even in 1+3, so I think it's kind of essentially still very badly understood how to even get the ODE system. Like how to write down the Einstein equations in such a way that I erase certain terms, like I erase these terms, and then get a nice system of ODEs. I don't think that's been done. Or okay, maybe it's been done, but
But isn't that what BKL did? No.
So the kind of perspective is a bit different. So BKL just say this. So BKL say, because I can erase those terms, I might as well assume my spacetime is homogeneous, and then they just study homogeneous spacetimes. So you can classify homogeneous spacetimes and then just say that in those classes, write down a system of ODEs. But that's not the type of perspective you can do in this case. You have to actually write down a system of PDEs and then erase terms.
Then okay, you have to do this anyway if you want.
Yeah, you certainly have to do this, but this is yeah. Understanding that system of ODEs may have been
But shouldn't it be sort of the same system, or is it not so clear? I guess it depends on the age and so on.
As I say, if you have homogeneous spacetimes, you can classify. You can say that I assume there's the spatial topology. And I assume that if I have this topology, then variables, and then I just study ODEs. So that's kind of not the way.
Christoph, any more questions? All right. So let's start the recording.